Alright, so welcome back to the next lecture, lecture number 19. Right, so in this lecture, we would like to see the speed control of DC motor, speed control of DC motor. So here, let us see that what will be the speed and how does it relevant to various things. So prior to that, whether it is generator or motor, we said several times it has same induced EMF. If it is generator, we represent as EG. If it is a motor, we represent as EB. So what we got, this expression is number of poles into total number of conductors divided by number of parallel paths is a constant into the flux per pole into the speed n, which is in rps, revolutions per second. So with this, can we say that the speed is proportional to the induced EMF in the motor, that is what back EMF, divided by the flux. So the speed is proportional to EB by phi. So we can say this proportionality constant as some k. So k into EB by phi. And we seen in the motor, like in separately excited, so or in shunt excited, let us say if the applied voltage is V, so V minus IA RA is what the armature voltage drop. So if it is subtracted from the terminal voltage, it gives the EB, so divided by phi. So but usually, as the armature resistance is small, so RA is small. So as because RA is small, this IA RA drop will be negligible. This is very small. So if it is very small, now can I say this has some constant k into, so V, so approximately by phi. So this is approximate, the speed is just k constant into V by phi. Now see that how can I control the speed of a motor. So here try to observe different things are available. One is the voltage which we are applying across the armature. Another is the flux which is there inside the stator core. So try to observe this voltage is relevant to the armature, armature, armature voltage which we are applying across the armature or across armature voltage. And what about this phi? Phi is relevant to the stator field flux, stator field flux. That means by controlling these two parameters, we can control the speed, or we can increase or decrease the speed by changing these two parameters, armature voltage and stator field flux. So in this DC machine, so we have these two controls. Let me divide that into two, like this flow chart kind of thing. So one is this speed can be controlled by using armature. So let us say that is what the voltage. So this voltage can be varied. How can we vary the voltage? So this voltage can be varied. So how can we vary this voltage? Is that, so that method we call armature voltage control or armature control method, armature control. And in this armature control, try to observe that, so when we were controlling the armature voltage, we should keep the other to be constant, so that the speed is only proportional to this armature. So like speed is approximately some another constant k dash into V, when, so when flux is maintained constant, when it is maintained constant. So the speed is just simply proportional to the voltage. As I vary the armature voltage, the speed will vary. That is one thing. This is one method, armature control method. So one more is the field flux control. So see here that, so we have flux. So this flux also can be varied. So how can we vary this flux? Let us see that. So this, let me say as the method name is field control method. Field control method. So when we are controlling the field, one thing you should remember, so the speed is equal to some constant k dash into 1 by 5 into 1 by 5. So if we keep v as a constant, then only it is just directly inversely proportional to this flux. So we can say n is proportional to 1 by 5 here. So here speed is proportional to the applied voltage. When one is constant, other parameter is maintained constant. So these are the two important methods in the DC machine. So the speed control method, there are two speed control methods are there. One is armature control, other is field control. Let us see one by one. So this first one, let us take the speed control of, I am going to consider here only the shunt motor. One can think of other motors also, no issue. So the speed control of DC shunt motor, this you will perform even in the lab, the speed control technique. So on the shunt motor, so on DC shunt motor. For this DC shunt motor, the first method, let us choose the variation of flux, or you can consider the first anyone, no issue. So variation of flux or flux control method or field control method, all are same. So you can use same word, field control or flux control method. So control method field control method. Okay. So now let us see in this. So we seen that the speed is proportional to 1 by 5. When this expression is valid, when voltage is maintained constant, this you should not forget. If voltage also varying, the speed is not directly proportional to 1 by 5. So that you need to keep in mind. So v must be maintained constant, otherwise your things will not go in proper way. Now how can we vary this speed? Try to observe here. For example, if I'll reduce the field flux, what is going to be happen as a result of this? The speed will increase. So if the denominator of this is reducing, the entire term going to increase, that means speed is rising. So how can we reduce this field flux? How is that? We know this is related to the field current. If is proportional to the phi. So if if is proportional to the phi, then what should I do to reduce the field flux? So I should reduce the field current. How can I reduce the field current? If I have any variable in the field winding, that is what? The field winding resistance. So if I increase this resistance, current will be reduced. So thereby flux will be reduced. So if flux reduces, speed will increase. So this is what the field flux control method. Indirectly, instead of varying the direct field, we don't have any control over the field, but a indirect control is there. That is what the field winding resistance. So if I'll increase the field winding resistance, the field current going to reduce, thereby field flux reduces, as a result speed increases. So what shall I do in this control method is that, so let me show the schematic diagram of the DC shunt machine first. So then let me introduce this corresponding control method. So there will be armature terminals with the brushes arrangement, and in which EB is the back EMF, REA is the armature resistance. These are common, and these armature terminals I will call as A and double A. So these are the things which we usually see here. And apart from this, we have the field winding, and now this field winding is also usually connected in parallel to this. So now the very important thing is that previously we used to consider the field winding resistance is RF. Now let us consider, so the field winding resistance is extracted out, or let us say in this some resistance is there, that is the default resistance. So what I do is that externally I am connecting some field winding resistance, where this field winding resistance can be varied, where this field winding resistance can be increased. So assume that initially it is kept at minimum, initially kept at minimum, initially kept at minimum. So then I can change the field winding resistance. So if field winding resistance is changed, I had shown you here, current will decrease. Which current? Field current. Then thereby flux reduces. If flux reduces, speed increases. This is what the speed control method. So let me finish this connection first. So this is going to be connected across the armature. Why? Because this is a shunt machine. So let me connect. So this is what the field current IF. So this is field winding. Let us say FF terminal. This may have internally small resistance. Excluding that, I am adding one external resistor. This is what the external. Okay, how much resistance? RF, some value I am considering that as RF. Now I could able to vary this resistor. As I vary this resistor, so the machine speed going to be varied. So let me put some more connections. As this is a motor, so voltage is applied across this. So let us say voltage of V, current of I, and armature current is IA. In this way, this is what the field control method of the DC machine. So one important feature you need to look here is that, so this external resistor, let me say the RF is initially kept kept at minimum position, minimum position, minimum position. So thereby the flux in the core, the flux in the core is rated flux, rated flux, rated flux. So as a result of this, the speed of the machine, of the machine is rated, is rated speed. Speed of the machine is rated value, rated speed, just rated speed. Now see consequence. So as if I want to vary the speed, what shall I do? I will vary this resistance. So how I will vary? So I will increase the resistor slowly. Next is increase, increase RF gradually, gradually. Thereby, as a result of this, what is going to be happen? IF will reduce. If IF reduces, what is the consequence? Field flux reduces. If field flux reduces, as a result of this, the speed will increase. Why? Because so speed is proportional to 1 by phi. If phi reduces, speed will increase. Now try to observe one important consequence of this is that you can increase the speed only above this rated speed, but you cannot control the speed below the rated speed. In this method, the drawback is that the speed can be controlled, the speed can be controlled, speed can be controlled only above rated speed, above rated speed of the machine. Why? Because one can reduce the flux, but one cannot increase the flux by this rheostat, additional external rheostat. As because once I add any resistance additionally to this field winding, field current going to be reduced, thereby flux is weakening. So flux weakening is possible, but flux enhancement is not possible by adding resistor. Thereby the drawback of this method is that we can control the speed of the motor only above the rated speed. So this is one important aspect of the speed control method of this DC shunt motor by using field flux control method. Okay. So let us see one simple problem relevant to this. So one example problem as like this. See here. So a 250 volts DC shunt motor. So that means the voltage of the machine is 250 volts. See here, I am showing the same diagram. Let me copy this diagram here. Why? Because these notations are very important, like which one we are considering as which quantity. So this is what the speed control method. So which speed control method? Field flux. So V is given. Next, armature resistance is given, RA 0.25 ohms. What else is given? On load on load, it takes an armature current of 50 amperes. That means when this got connected to any load, here some mechanical load, this is what the load. When it is connected to the load, the current drawn by the armature is 50 amperes. Okay. Next, at this load, it is running at a speed of, this is C, RPM. If it is RPM, use capital N. If it is RPS, use small n. So 750 RPM. The flux of the motor is reduced. See what we are saying? We are weakening the flux of the motor. Thereby, we can increase the speed. This is what the field flux control method. So, the flux of the machine is reduced by 10 percentage. What does it mean? Let us say initial flux is phi 1. So, the new flux, what I am doing is that 10 percentage I am reducing. So, how much percentage is left out? 90 percentage left out. So, 0.9 into phi 1 is what the new flux. This you should understand very carefully. So, changing without changing the load torque. There is no change in the load torque. Find new speed of the motor. New speed of the motor. So, what we need to do? This is the speed N1 when it is drawing a current of this much when the flux is phi 1. So, the second case is what? When the flux is reduced by 10 percentage means new flux is phi 2 which is equal to 0.9 phi 1. So, what will be the speed of the machine? Under this condition, he said that the load torque is constant. The torque is maintained as constant. And we know that the armature torque TA is proportional to the flux and the armature current. So now can I say this as TA is constant, so TA1, that means case 1, this is case 1 data, N1 speed phi 1 flux is case 1, N2 speed phi 2 is what, case 2. In case of case 1, so torque is TA1. In case of case 2, torque is TA2. So now can I write this as, so phi 1 IA1 is equal to phi 2 IA2 from this above expression. So some things are given. Let us find what will be new armature current when it runs at new speed. So that IA2 is equal to so phi 1 by phi 2 into IA1. So IA1 is given to us. What is IA1? This is what IA1, 50 amperes. So this phi 1 is, let us say phi 1, phi 2 is 0.951 and IA is 50. So how much is this amperes? So you will get this as 55.6 amperes. That means current is increasing. See, from 50 it is increasing to 55.6. This is what IA2. Now, let us see the EB expression, induced EMF inside the machine. EB is equal to V minus IA RA. This is what we know, generalized expression. Now, can I say the induced EMF in case 1 is EB1 when a current of IA1 is flowing. In the same way, in case 2, an induced EMF of EB2 is generated when a current of IA2 is flowing. Remaining things are constant. See this. So now what will be this EB1? Let us calculate. EB1 is equal to V is given as 250 minus IA1 is 50 into RA is 0.25 ohms. So how much you will get this? Just calculate it. So you will get this as 237.5 volts. This is what EB1. So why are we calculating this EB1? We will see just in the next step. So what about EB2? So let us calculate 250 minus, so IA2 is 55.6 into RA is 0.25. So how much is this? So this one gives as 236.1 volts. So small reduction in the back EMF here. So now use these two values. What we know, EB is proportional to flux into speed. Now we know that flux is reduced, thereby speed going to be increased. How much is that increase? So from this relationship, so we can write EB2 divided by EB1 is equal to, so phi 1 phi 2 divided by phi 1 into n2 divided by n1, a simple proportionality relationship. So if I substitute all known things, EB2 is 236.1 divided by EB1 is 237.5, so is equal to phi 2 is 0.951, phi 1 is same as phi 1, n2 that what I need to calculate what will be the new speed, and n1 is how much is the n1? N1 is 750 rpm, n1 is 750 rpm. So if we just see this, these phi 1 will get cancelled. So if you calculate this n2, you will get, so I got this as 828.4 rpm. See that if I'll reduce the flux by 10 percentage, the speed has increased from 750 to 828.4 rpm. So when you weaken the flux, that is what the field flux control method, when you reduce the flux, so the amount of the current is going to means the what we can say is that when we reduce the field flux, that flux is going to be weakened, that in turn increase the speed, as because flux is inversely proportional to the speed. Clear? So this is one of the important aspect of the speed control. Just take some more problem to get better awareness on this technique. And now let us see the next technique, which is the armature voltage control, or simply armature. Let me say the second method. The second method is armature, or we can say rheostat control method, armature or rheostat control method. So with this, what I am trying to do is that I would like to vary the resistance so that the armature voltage going to be vary. So let me show first that corresponding schematic view. So before that, so let me show initially that schematic view. So first what I'll do is that to save the time. So let me take yeah. So this same diagram some extent. So just I will do some modifications. Just observe that what modifications I am doing. So just to save the time, I am taking that same diagram. So see here, I don't want any field rheostat here. So let us remove that. So this is not the field flux control. So I am putting just simply field winding. So in this, there may be field winding resistance internally. I am not adding any external resistance. So what additionally I will do is that just I will add here, some, so field resistance, sorry, some armature resistance. So in series with this, so this can be variable. This is what the armature external resistance, armature external resistance. You can say, to avoid the confusion, previously also this as ext, previously also you can assume here as ext, no issue. Even I had written that ext, see here. So you can consider this is what the R external, and this field winding may be as usual. So this may be as usual. Now this R external plus RF is what the total field winding resistance. Clear? So right. So here also R external plus REA, which is already there, together is what the armature resistance. Now where shall I connect this field? Field winding should be connected always across the power supply. So I connected across the power supply. See here. Now as I vary this R external, what is going to be happen? See this. This is what the armature. So let me say here to here to here is what the armature voltage VA, armature voltage VA. So now I can control this VA. VA can be varied. How? VA can be varied. How can we vary VA? Check it. So if R external in the armature is varied, if R external in the armature is varied, so this VA can be varied. Let me put the arrow mark in reverse in this way. If R external is varied, VA will vary. How? Let us see in this way. So can I say, if this current is armature current, IA. So see this, I am applying a constant voltage, no change in that. But how much armature voltage I am getting is that, so V, that is the applied constant voltage, minus IA into R external, R external. Now see here carefully, if this R external is varied, what is going to be happen? IA RA going to change. If IA RA changes, VA going to be changed. And we know that we had seen previously, the speed is proportional to the armature voltage VA. So what is VA? VA is, let me write here, armature voltage. Armature voltage. Previously, when R external was not there, if R external is made 0, VA, armature voltage, is equal to supply voltage. That's why previously I might be written this N is proportional to V. But now I would like to make this VA to be variable. In order to make this VA to be variable, I connected one resistor in series with the armature, so that armature current can be controlled, or just this drop can be controlled. If this drop can be controlled, VA can be varied. So thereby speed can be varied. But one thing you should assume, let us say in this way. So initially, let us say initially the RA or R external resistance is kept at minimum, that is 0, minimum. So if it is kept at minimum, so what is its corresponding speed? The speed of the machine is what? The rated speed. Why? Why? Because the armature voltage is equal to rated voltage which we are applying. This is what? The rated voltage. VA is equal to V rated. So next, if R external is increased to maximum value, increased to maximum value, what will happen? VA is going to become minimum value. Why? Because IA into R external will reduce. If R external is increased, so this entire term going to reduce. Why? Because this drop is increasing, V minus IA R external is reducing. As a result, VA is reducing to minimum value. So if VA reduces, we know the speed is proportional to VA. So if VA reduces, one thing you can conclude that as VA reduces, the speed also reduces. Now see that. So what can we do in the armature voltage control method? We can control the speed from rated speed to below, not above. See, speed is reducing here. From where? From rated speed. So just let me add this point here. In the armature control method, the speed can be controlled. Speed can be controlled controlled only below base speed, below base speed or rated speed, base or rated speed. Whereas in field flux control, above base speed. These two points are very important for competitive exam. Which method is used for which purpose? So these are very important, and see that. So this is one generalized thing, and just let me take its corresponding problem. So as an example, so see here again, let me put up everything, the given data. So here a 200 volts DC machine, that means V is equal to let us say 200 volts. So next is let us see, uh, at 200 volts and running at speed is 1000 rpm. What else is given? Armature current is IA. How much is that? 17.5 amperes. So it is required to reduce the speed. Let us say this is N1. Now the next data is N2. N2, how much is the speed required? 600 rpm. So what must be the value of the resistance to be inserted in the armature circuit if the original armature resistance is 0.4 ohms? That means RA original is given already, 0.4 ohms. So how much additionally I need to put on that? That is what the external resistor. so that the speed is reduced to this value. So it is below base speed. This may be rated speed. So below that speed I want to bring the machine. So take the armature current to be constant. So in this process, see that armature current IA is constant. Armature current IA is constant. Okay. So now let us see what are the relevant expression. Just simple thing, you need to look on these more specifically, the diagram. The diagram. So let me take this diagram. Let me take this diagram. So whenever you see these corresponding control methods problem, numerical problem, always draw beside that corresponding diagram, so that a better idea or better understanding can be achieved on that problem. Okay. So right. So this is the corresponding diagram. So what are the things are given? RA is given already. How much external resistance I need to incorporate here? Okay. So when or let me say in this way. So can I say the induced EMF in the armature EB is equal to V minus IA into R or total, let us say RT. Let me write here what is RT is. RT is our total armature resistance, which is equal to RA plus R external. RA plus R external. So this external resistance drop and internal armature resistance drop, once we subtracted from this terminal voltage V, the left out voltage is what? EB. So that what I am saying. So this voltage how much we will get? Let me say EB1. EB1 is equal to 200 minus how much is the armature current? 17.5 into R, let us say initially so this R external, like let me say here it is, or let me write directly. So I will give the explanation beside it, is equal to 0.4. Why? Because see here, initially I told you, initially the R external is kept at minimum. What is mean by that minimum? 0. So if it is 0, what will be the RT? RT is equal to simply RA, which was the internal resistance. So that's why here I considered only RA, since this is what the explanation. So initially this is the R external position. Next is, so how much is this value? Let us calculate. 200 minus 17.5 into 0.4, around 193 you will get. Just cross verify. I verified this. EB1 is equal to 193 volts. Now, so what I am going to do is that I am going to increase this R external. As a result, some speed is going to be reduced. What is its corresponding speed? Is 600. Now let us see what is its corresponding induced EMF in the machine. That is EB is equal to 200 minus same armature current. They said armature current is maintained constant into R total resistance. What is R total here? RA plus R external. Okay. So let us see what will be this EB. Now let us keep as it is, as because this RT is unknown. Now we know that so for a shunt machine, ISH is equal to V by RSH field winding. So this will be almost constant. If this is constant, field flux is going to be constant. So this condition is maintained. See here. So when we were controlling by the armature voltage, the field flux must be maintained constant. So this field flux is constant. If field flux is constant, we know EB is proportional to the flux and the speed. So now can I say that EB is proportional to only speed? Why? Because flux is constant. So now from this, can I write the proportionality relationship? EB2 divided by EB1 is equal to N2 by N1. So once you know these EMF expressions, many things are very easy, and remaining is simple as like circuit analysis part. So this we can write in this way. So EB2 is 200 minus 17.5 into RT, capital T, divided by EB1 is known. How much we got? 193, and its corresponding speed we need to know, or which is already given. Sometimes this speed may be asked to calculate. So N2, how much is the reduced speed? 600. So N2 is 600, N2 is 600 divided by N1 is 1000. So if we calculate from this expression RT, so that RT we get this as 4.811 ohms. 4.811 ohms. But what is RT exactly? Internal resistance plus this external resistance which we need to add to bring the speed to 600 RPM. So RA is already known. So can I say this external resistance which I need to add is that 4.811 minus RA, which is equal to 0.4. So this gives as 4.411 ohms. So this amount of the external resistance need to be added in series with the armature to bring the machine speed to 600 rpm. Okay, so this is what the armature voltage control method, so which you can just visualize by this problem. So simple, but you have to carefully observe what is the difference between these two methods. Armature voltage control method can be control the speed only below base speed, whereas field flux control method can be used above base speed. So when we use combinedly these two, that may be added advantage to control the speed of the machine over below base speed to above base speed. Okay, so that you can also do that thing. And one more thing you should carefully observe. So when I said these instructions, so see here, initially this is kept at minimum, which resistance, which resistance, this is what armature resistance, external resistance, whereas the field control method, so the important point in that is that the external field resistor, the external field resistor is kept initially at minimum position, initially at minimum position. Okay, so just this is like, let me say, so with respect to this experiment, so these are the things going to take place. Okay, so just when you are doing in the lab the corresponding experiments, just read the procedure to do the experiment and just try to interpret this theory with there and try to get maximum inputs out of these two methods, and which are very important. Okay, thank you.